Here we go. Welcome everyone to this week's edition of HoloTube. We feature this time Erik van Heumen. Heumen, right? Is that
Heumen,
how?
yes, Heumen.
When I speak English, I don't know any Dutch and German anymore. So, but yeah, we are very happy to have you here and to tell us about your work on quantum matter. In particular, your title, it talks about probing low energy quantum matter, and I suppose you will be too. So thank you for being here, and please take it away.
Thanks very much for the invitation. And yeah, I kept the title that I sent, but it actually should have a subtitle. It should say probing it with optical spectroscopy. But that will become clear, I guess, in the remainder of the talk. So before I start and before I forget, I'd like to thank my two PhD students, Xuanbao Feng and Silvia Castanelli. So they did most of the experiments, well, all the experiments actually. I don't get to do those very often anymore. Most of the talk is work that I did in collaboration with Jan Zane from Leiden University. And in the beginning, I'll show you some data on charge density wave system that was made in the group of Enrico da Como at the University of Bath. So maybe I want to give you a brief outline. So what I would like to talk about today is about high temperature superconductors, or more specifically about the strange metal phase that appears in these materials. But before I do that, I want to introduce the main technique, which is optical spectroscopy, which is used in my group. And optical experiments are quite nice because from the frequency dependence of the optical conductivity, you can obtain a lot of information on the collective response of systems. So the pictures you see here in the phase diagram are angle resolved photo emission experiments where you probe the excitations, let's say the single particle excitations of the system. And it's believed that when interactions are really strong or when the system is strongly correlated, that the collective dynamics contains additional information that you cannot easily extract from single particle excitations. And so in that sense, it's a nice complementary tool. At the University of Amsterdam, we do both experiments. So for example, this image on the right here and the one in the center are from experiments that we did in the past 5 years. And this is in collaboration with Mark Golden. And then in my own group, I also do optical conductivity experiments. So before I tell you something about the cuprates, I want to show you a little bit about how these experiments are done. Some of you already know this. I know Sasha does. Maybe Matteo also remembers. I think I talked about this in more detail earlier this year, but others may not. So I'll briefly go through how such an experiment works. Because the optical conductivity is not something you can easily measure directly. And so the thing that you actually measure in most experiments, there are actually two experiments. You can also do ellipsometry, but I won't discuss that. But in the experiments in my group, you basically shine light on your material and then you measure the reflected intensity. And then after you've recorded part of the spectrum, you cover the sample in gold, which in the infrared is a close to perfect conductor and therefore almost a perfect mirror. And then you take the ratio of these two numbers, and this gives you a percentage, the reflection of the sample. And so that's what's shown on the right here. This is for a particular wavelength range. And what you can see is that there is the reflection approaches 100% at low energy. At higher energies, it has some frequency dependence. There are maybe a few weak bumps here. These are actual phonons. Get to that in a little bit. And then you see lots of noise on the sides. So this we usually ignore. And so in one experiment, we can measure a small wavelength range. And then we repeat the experiment for different wavelength ranges and then put everything together so that we cover a broad part of the photon energy range in our group. So typically, for those of you who work in real units, this is in my group between about 5 milli-electron volt and then all the way up to 4 electron volt. So reflectivity data usually doesn't say so much to people. So I'm going to give it a try and tell you a little bit about it anyway. So I wanted to show you 3 examples. And the first one is a high temperature superconductor. This is the specific material. It's a superconductor with a critical temperature of 23 Kelvin. And here you see basically the frequency dependence of what is a metal. And so for those of you who remember from the Drude model what the plasma frequency is, the plasma frequency you can almost read off here. The plasma frequency is the minimum in the reflectivity. So it's around 1 electron volt in this case. It's not exactly the plasma frequency, but that's a detail. You can see that this is a metal because the reflectivity extrapolates to 1 at 0 frequency. So for a metal, if you measure the reflectivity, you would expect a reflectivity very close to 1 and at 0 frequency exactly equal to 1. Now I wrote here that this is a bad metal, and you can't, well, maybe you can't see it from this graph, but I can. So then the question is, what does a good metal look like? If you would plot the reflection of gold on the same scale, I've exaggerated a little bit here. It's almost exactly equal to 1. There's a very small deviation from 1. I've actually enlarged that deviation a little bit. So the reflectivity of gold in the energy range up to 1 electron volt is essentially equal to 1. That's why we use it as a reference, of course. And the deviation from 1 essentially tells you something about the scattering rate that the electrons have in this material. So I'll get back to that on the next slide. So this is more or less the reflectivity of a metal. And then the next material I wanted to show was this one. This is an insulator. It's actually a not so interesting material because nothing really happens in the temperature range where we measured it. But at slightly higher temperatures, this becomes an ionic, a super ionic conductor. It's possibly a material that's interesting for applications in battery technology. And so measuring the phonon spectrum is what we were after. So here you see again the reflectivity. And in contrast to what you see in a metal, the reflectivity is very low almost everywhere. And actually at low energies, it doesn't extrapolate to 1. So the key difference between an insulator and a metal that you can read off from any spectrum that you see is that the reflectivity of an insulator is very small and goes to 0 at a finite number, whereas at a number smaller than 1, whereas the reflectivity of a metal extrapolates to 1. That's the key difference that comes out of essentially through the model. So these line shapes that you see here are optical phonons, and here they're really quite large. I promised you to show a little bit more also later about optical phonons in cuprate data. They are actually here. And you can't see them because the free electrons are actually screening these excitations. And so, you know, that's another one of the differences. Now, funnily enough, the reflectivity of this insulator is higher in the visible light as compared to this metal. And so if you would actually look at these 2 materials with your own eyes, this would actually reflect a bit less, and it would actually look like dark, like a black mirror, or well, more or less it would look like something like this, like my iPhone. Whereas if you look to this material on the right, it reflects a lot more, and moreover, it has some structure in the visible range of the spectrum. It actually looks like a silver mirror. So even though this material is an insulator, it to your own eyes, it would appear more metallic actually. So that reading these reflectivity spectra is actually not so obvious. So now comes a more complicated one. As the name of the slide suggests, I wanted to say something about spontaneous symmetry breaking. So here is a material, vanadium diselenide. This is a widely studied material that is one of these layered van der Waals materials. And this undergoes a phase transition to a charged density wave state at 112 Kelvin. And below that temperature, you see something happening. So at high temperatures, it's a metal. So you can see the red data, it sort of extrapolates to 1. It's not completely obvious on this small scale. But then as you go into the charge density wave state below 112 Kelvin, so the black curve is at 16 Kelvin, you see that the reflection actually goes up very steeply and is almost exactly equal to 1 over a very small energy range. And then you can see these strong oscillations here. These are again optical phonons, just like you see here. And so very surprisingly, the reflectivity of this material looks like a very good metal, yet the phonons appear unscreened. And so somehow this is somewhere in between what you see for a metal and an insulator. And I wanted to briefly explain where the difference is coming from. So in order to understand this, it's actually more useful or easier to go to the optical conductivity of these three materials. And so they're shown here all together. So let me start from left to right. So in the band metals, you have a Drude response. So if you remember from maybe, I don't know, I'm teaching this in third year solid state physics. If you take a metal and you apply an oscillating electric field, then the free electrons will start to oscillate with the electric field. And because they experience some scattering, there will be a damping rate associated with this oscillation. And this gives rise to a Drude response. So that should be a Lorentzian centered at zero frequency. And the width of this Lorentzian is the damping rate that the electrons experience. So what you see happening here is that at high temperatures, the damping rate is quite large. And as you decrease temperature, this peak becomes narrower and narrower, it sharpens up, and the damping rate is decreasing. So I'll get back to an analysis of this in the second part of the talk. What you also see here is an upturn at higher energies. This is the onset to interband transitions in this material. But because it's a metal, you see a Drude response. It's very different in the insulator. Note that there is a factor 10 to the 3 difference in the two scales here. So if you look at the insulator, you see that the conductivity is much lower, which you might expect. It's an insulator. You see these phonon modes. And then at higher energies, you also see an interband response. And this is what gives rise to the colors, or to the silver color that you see with your own eyes if you look at this material. But the important thing is that there is a gap here that you can see in the optical conductivity. And then beyond that, there is a peak which is due to interband transitions. So now let's go to the charge density wave system. And what you see there is that at room temperature, it's a metal and there's a Drude response. It has a width, it's a lot smaller than, well, it's not a whole lot. It's a little bit smaller than the cuprate on the left. And as you go through this phase transition, you see that the Drude response is gapped out and you get a big peak. It's at low energy, so it sits at around 0.1 electron volt. And on top of that peak, you see these very sharp structures. And these are optical phonons. And so this very much, the black curve very much resembles the response of the insulator, except with a much narrower gap. And if this was the only information you had, you might conclude that this material somehow becomes an insulator as well. And this makes sense. I mean, when you go into the charge density wave state, you open a gap at the Fermi level. And so you gap out excitations and essentially you get an insulator. Yet the reflectivity looks very different. And actually the reflectivity was very close to 1 below this energy range. So how come? Where does this come from? And so I want to give a very naive picture for this, which comes from just basic textbook physics, essentially. So imagine you have a linear chain. It's a perfect chain, and you compute a tight binding spectrum for this. Put one orbital on every side and one electron in it, and then you have a half-filled band. So you have a simple metal, and the optical conductivity for that should be a Drude response. Now, if we dimerize this system, we open a gap at the Fermi level, and instead what we get is optical excitations which are gaps, and the energy, the gap in energy is 2 delta. But in addition, we get Goldstone modes because we've spontaneously broken translations. We get a Goldstone mode, and this is a 0 energy delta function response in the optical conductivity. I can't measure this at finite frequency. So in my optical experiments, I'm always looking at finite frequency. So I can never see this, this delta function at 0 energy. And so therefore, the only thing I see and what it looks like is this insulating state. Now, that's of course not very nice. I would like, to really also try and see if this Goldstone mode is there. And moreover, it's something that should show up somehow in the experiment because it's there. And it does, just not in the real part. So the trick around this is to instead do Kramer's Kronig transform, put differently, make use of causality, because when you Fourier Kramer's Kronig transform this delta function response, you get a dielectric function that diverges as 1 over omega squared. And that's in contrast to the Kramer's Kronig transform of the Drude response, which essentially gives you a constant. And so if you take the Kramer's Kronig transform of your real part of the optical conductivity, multiply it by minus omega squared, then in the charge density wave state, you get a function which extrapolates to a constant, whereas the Drude response extrapolates to 0. And from my reflectivity data, I can obtain both sigma 1 and epsilon 1. And so when I do this for my in experiment, I already showed you the real part of the optical conductivity, but I can also compute the imaginary part of the real part of the dielectric response, and I multiply this with minus omega squared, and then look at the extrapolation to 0 frequency. And when you plot that extrapolation, so here I didn't really extrapolate it, I just took the value of this function at 10 millielectron volts, so the lowest data point. You indeed see that there is this onset at the critical temperature, and this is a measure of the density of electrons participating in the collective response. So causality, the fact that this is a causal response function is actually very useful. And something I want to use in the second part of this talk. So maybe a brief pause here to take a sip of water. Are there questions so far? Okay. So then to the actual experiments that I wanted to show you today. So in the cuprates, so I've just tried to show you how you can extract useful information from optical conductivity experiments, especially through Kramer's Kronig relations, or the fact that this is a causal response function. And so I wanted to use that also in the cuprates to try and answer some questions that have popped up over the last few years. And the first question is shown here. So in 2016, it was reported that if you look at the carrier density obtained from Hall experiments, so where you take a cuprate and you put it in a magnetic field and then measure the transverse voltage that develops, the Hall voltage. If you look at the doping dependence of that Hall voltage, you can essentially, the claim is, extract the carrier density. So that's NH, the carrier density extracted from Hall experiments. So at low doping, you see that it increases linearly with the number of holes per copper oxygen plaquette. As you might expect, it goes to 0 exactly at Hall filling, where you have an insulator. And then there's a range where something else interferes, charge density wave physics in this particular material. This is LSCO on the left here. But then if you go close to optimal doping, you see that the Hall density starts to increase and it goes to a value which is 1 plus P. And it happens around a doping, which is around 0.2 holes per copper. On the other hand, experiments from a competing group were showing slightly different behavior. It is a different material. This is LSCO on the left, and this is thallium-2201. They also see a change in the carrier density, but it's much more gradual, and it seems to extend over a much larger part of the phase diagram. And then finally, there were angle resolved photo emission experiments done in Stanford, where people looked at the antinodal direction and found that changes in the line shape were very sudden and took place around 0.2, well, a little bit lower than 0.2 holes per copper. So there are now two different sets of experiments that should show the same physics, but don't. And so I wanted to see if optical spectroscopy could be a useful way of probing the same collective dynamics and to see whether either of these pictures was correct. Now, this is actually not so easy. In the last 30 plus years, there have been many optical experiments have already been done. And there are generally two schools of thought to interpret optics data. And it boils down to one versus two components. So in the single components picture, people assume that the Drude response that you see is an indication of quasi-particles with residual interactions. And maybe there is an energy-dependent lifetime broadening. So as you probably know from simple perturbation theory, or sorry, diagrammatic perturbation theory, as you start adding self-energies, you introduce an energy-dependent, frequency-dependent lifetime. And this changes the simple Drude response to something with a different frequency dependence. So this can be captured roughly in the following way. You can write not just a simple Drude response, but instead write this function, which is called the extended Drude model, which is more or less the same, except that there is this energy and temperature dependent scattering rate, or memory function, I should say. It contains not just the scattering rate, but also mass enhancement. So that changes the line shape that you should see in experiments. And that is contrasted by this second picture, where the optical conductivity is basically believed to consist of two components. Generally, people argue that this is an indication that there are no longer quasi-particles. There are strong interactions, so that should not be residual. And people observe mid-infrared bands and possibly also a little bit of lifetime broadening. Maybe a little bit similar to this, but typically not. And I think, as I'll show you in the rest of the talk, in this case, if you analyze it in a two-component picture, the lifetime becomes actually frequency independent. So very roughly, there's really two contrasting pictures here, because in this case, you assume that the optical conductivity can be written in the following form. So you have two components. There's a Drude response, and then there is some mid-infrared band or incoherent response. And so distinguishing between these two cases is difficult, and this is where causality and Kramers-Kronig relations come in, as I'll show you next. So it's not a new story. These two interpretations have been tried in the past. This is one of the older works from my thesis supervisor, Dirk van der Marel, 1991. He was already analyzing high temperature superconductivity data, superconductors using a single component picture more than 30 years ago. But in the same year, people were also looking into this two-component picture. So this is work from Uchida, and she shows that there is maybe another alternative interpretation where you have a mid-infrared band. So the energy scale here, this is roughly 125 milli-electron volts. Sorry. Now the properties of this mid-infrared response are actually quite interesting. And so in 2003, it was Dirk van der Marel together with Jan Zane who showed that maybe this the optical conductivity in the mid-infrared follows a 1 over omega to some power dependence, so really different from the Drude response. And this power law dependence, according to them, was a signature of a quantum critical state. And so this is sort of the latest in 2003, and since then, no big new breakthroughs have been reported in this direction. And in the last 2 years, actually, there were 3 optics groups that came out with new analysis, new data, and my group is one of those. And so those are the results I wanted to show you in the remaining 10-15 minutes. All right, so the material I'm going to show is a single layer cuprates. The crystal structure is shown on the right here. So you have a single copper oxygen plane in the unit cell, and that makes life relatively simple. For optical experiments, it doesn't matter so much whether it's 1, 2, or 3 layers, but really it makes it, it removes any worry about possible interband transitions between bands that come from this bilayer splitting, for example. So that's not a thing to worry about. It's particularly nice also because we do photo emission experiments on these materials, and the analysis of that is a lot simpler. Another nice thing about this material is that it has a low critical temperature. So we have a large temperature range over which we can look at the normal state, at the strange metal phase. It has a good cleavage surface. So if you have a nice big crystal, you can just, with a Scotch tape, you can peel off a few layers, and then you're left with a very nice reflective surface on which you can very nicely do optics experiments or other experiments. And so in this talk, I'll show crystals that we've made ourselves. Those are the blue dots. Some crystals that I measured on crystals from Aisaki, that's in red. And I also got some one crystal from Takeshi Kondo. And so together we cover the entire superconducting dome. There are 2 crystals that are, well, they're placed exactly at the endpoints. To be very honest, I don't know the doping exactly. They don't show superconductivity, so they probably fall a little bit outside of the dome. All right, so here are 4 representative sets of spectra, starting in the underdoped side, going close to the most overdoped crystal. Basically, you see a Drude response at low frequency. So you see this plateau here. This is on a log scale. And so if you just plot a simple Drude function, you essentially expect a plateau and then a fall off with the characteristic 1 over omega squared frequency. So in other words, the slope here should be -2. Just a point of note, the extrapolation to 0 frequency gives you the DC conductivity. 1 over this number should, of course, be the resistivity that people measure in experiments just by sticking wires and passing a current through. And this actually corresponds very nicely with what we've obtained on these same crystals. If you look closely, however, at low temperatures, so that's, for example, the blue curve here is the most obvious, but we see this at all dopings, you see that there is a change in frequency dependence here. And that hints at 2 components in the intraband response. Note the interband response, so optical transitions between 2 different bands. Those are only expected for energies larger than 1 electron volt. You can actually see them here in this graph. And so there really is no expectation to see interband transitions at lower energy. And so this really suggests that the intraband response really consists of 2 components. The crossover between these 2 components is around 0.1 electron volts, and that doesn't seem to depend much on doping. So both at the underdoped side and the overdoped side, we see it around 0.1 electron volt. And so I wanted to check first how close the low energy Drude response actually was to a Drude response. So in other words, for the real part of the optical conductivity, if it's a simple metal, you'd expect something like this, where the frequency dependence has this exponent 2. And so one thing you can do is you can take the logarithmic derivative of the log of sigma 1, and that function should then have a value of -2. So that's this function that I'm plotting here. The color scale here is going from dark blue, which is 0, to -2. And you see at optimal doping, you see that indeed at low energies, there is a range where the optical conductivity is very close, if not equal to -2. And then just below that, it goes to 0. And this Drude response is visible in the data up until about 150 Kelvin. Now, I've measured many more data sets, and you see that, well, maybe there is something here. This, at low dopings, the width of this peak, which I get from a different analysis, is so large that you don't see this 1 over omega to the power 2. This is actually hidden below the second component. But at higher dopings, we clearly see, at all other dopings, we see that there's a clear Drude response at all dopings, and it always seems to disappear roughly around 150 Kelvin. So that's the low energy response, that's Drude. And then the high energy response has a different frequency, as I said. And you can, by plotting the absolute value of the conductivity, you can extract the frequency dependence of this. And you should find then some exponent alpha. And you can sort of read that off here. But it should also be accompanied by a constant phase angle. And so this is only a real power law dependence if there is indeed a constant phase angle. And so here are 2 examples shown. I could argue, well, you know, I take this blue curve that's very nicely constant in the entire high energy range, but that would be the only curve on the entire slide, really. And you can also see that at low energy, there are some deviations, but especially at high energy, it's more curved. And at low doping, the curvature becomes even larger. And so that doesn't seem to be a very clean power law dependence. And so we wanted to see if this is really a power law, and if so, what were the parameters of this power law? So what is the exponent, and what else can we learn from this, or where is this curvature coming from? In order to do that, we made an assumption about the shape of this incoherent response. So we assume that there are indeed 2 components. The first one is simple Drude, so that one is easy, we know what it is. However, the second component, if this power law is correct, then both sigma 1 and sigma 2 should diverge. So this is where causality comes in again, because here I'm plotting both sigma 1 and sigma 2, the real and imaginary part of the response function. Well, you might say that sigma 1 actually diverges. Sigma 2 clearly does not. So this power law function really is not the correct description of this data. And so after a little back and forth with Jan Zane, we eventually came up with the following form for the incoherent response. And this is, we dubbed this a generalized interband transition, because for a value of alpha equal to 2, this form exactly is an interband transition. But in this particular form, it's slightly different. So it has 2 interesting features. The first one is that at high energies, it indeed goes to, it extrapolates to this power law dependence that is experimentally observed. But interestingly, it also has a low energy extrapolation, which is also a power law function, but with a different exponent. And so with this function, we tried to fit the optical data. So now I have a combination of a Drude response and a power law response. That's the 2 black curves here for the real part. and the 2 pink curves are for the imaginary parts. And with these two, with this, I can actually reproduce the both the real and imaginary part of the experimental data very nicely. And then we can look at the values of some of the parameters that come out. So in particular, the Drude weight, the Drude scattering rate, and the parameters of the incoherent response. So from the Drude weight, we can extract the the carrier density, and this can be compared again to the Hall carrier density that I showed a couple of slides ago. So just from these total spectral weight or total Drude weight, we see that it tracks the line n equals to 1/2 plus p. But the Drude weight, so the spectral weight contained in the dashed curve here, if we plot that as a function of doping, it tracks exactly the line n is p. And note in the transport experiments, people saw a change starting to take place at 0.2. In our experiments, we don't see any of that. So in optical experiments, the carrier density just continues monotonously without any change happening. As I already mentioned, there were other experiments that came out roughly at the same time. So here I'm showing one of them. This is data from the Maro group. They find a slightly different doping dependence, but just note that I'm just plotting my data only in the blue square here. So this is the same range of dopings. And in this window, they also don't see an obvious change at P star, which is the red line here. So I think our experiments are actually consistent with each other, given the error bars that are involved. So we can also extract the scattering rate. So that's plotted here, and it changes with doping. So the most overdoped samples have the lowest, the smallest Drude width. And as doping decreases, the scattering rate goes up, and it follows more or less linear in temperature dependence. Actually, if we combine these two numbers, Drude weight and scattering rate, as function of temperature, then that should reproduce the DC resistivity, and indeed it does. So if I take from my optics experiments the Drude width and Drude weight, I can, without any further scaling, get very good agreement with measured resistivity on such crystals. All right, so what about this strange, the incoherent response? So it's best seen in the phase angle, actually. So of course, because I get a good fit between to my optical, to both the real and imaginary part in the experimental data, I also get a good fit of the phase angle. But there's one surprising thing that comes out of that, and that's that the exponent of the mid-infrared contribution that is being put into the fit is actually a lot smaller than the exponent that you would get if you read it off simply from the experiment. So in the experiment, you would guess that the exponent is 60 degrees, which corresponds to an exponent of 0.66 or 0.65, roughly something like that. Whereas if you do the analysis, because of the way that the Drude and mid-infrared component interact with each other, the actual exponent that you put in is a lot smaller. And so instead of a phase angle that's around 0.6, from this decomposition, you actually find that the phase angle is around 0.5, and goes up a little bit as you go towards the overdoped side. Oh yeah, and the other factor that we extract is the weight in this mid-infrared component, and this is more or less doping and temperature independent. All right, that's more or less all I had to say. So I hope that I've convinced you that there are two components in the optical conductivity of cuprates. I've summarized the properties of these two components here. And the interesting thing is that this incoherent response really persists from very low dopings all the way to the most strongly overdoped samples that we've measured. And if you believe that this incoherent response is a signature of interesting physics, then actually what our data shows is that that this strange metal physics may persist over the entire doping range, in at least in single layer BISCO. And another thing is that the optics and normal state transport agree. And so there is still this discrepancy between both the Hall experiments. And then of course you have to realize that the Hall data is measured in large magnetic fields. In order to extract this Hall number, people actually apply 16 to 30 Tesla magnetic field. And that may actually change the physics. And so one of the puzzles is to connect the optics data to these high field transport experiments. This is some of the stuff that we're currently working on. With that, thank you very much for your attention, and I'll welcome any questions you have.
Thank you very much, Erik, for this very interesting talk from an experimental point of view this time. Thanks. So, other questions?
Can I ask? I might have missed it, but so you're using this modified line shape for the second component with an exponent beta in the denominator.
Yes.
But what is the value of beta which you get, and does it depend on anything?
Yeah, it's actually well, okay. So it's related to alpha, and I think it's I forgot the exact relation from the top of my head. It's something like beta is alpha plus 1/2 or something. I think it's alpha plus 1/2. So you can basically read it off here. The actual exponent, sorry, give me 1 second to find the right slides for that.
I see. So you're basically talking about phase angle, because phase angle is
Yes,
is an avatar of beta.
Yeah, exactly. I mean, it's right. It's here. So it's the combined exponent of this square root with the beta. I think it's alpha plus 1/2.
And what is your judgment? So it changes somewhat within the scope of the dopings which you have. But
yeah, so
would we say that this is like almost constant, or would we rather say that we see some trend?
no, I don't think these error bars are, I think, on the happy side. So if I would be a bit more conservative, you could basically say that it's more or less constant up until I don't know, somewhere here. And then maybe, I mean, I'm pretty sure that there is an increase in the highest dopings. So it seems to increase, but I cannot say. So is whether it's a continuous trend, like a linear regression through these data points, or whether maybe something is happening around this critical doping that seems to be there in all the other experiments, which is exactly in this place where I don't have data. Right, so there is something happening in angle resolved photo emission experiments and transport experiments around a critical doping of 0.2. That happens.
Yes.
And experiment is experiments, and these experiments are not wrong. It's maybe the interpretation that we give to them, at least to the transport community, that could be incorrect, because again, I don't see changes in the carrier density. So something else must be changing. And yeah, maybe it's something that maybe there's a change here in this in what happens with this incoherent background. But unfortunately, I'm missing maybe a few data points here, and so I cannot really say that yet.
I also have questions, but it looks like Navid also has a question. So Navid, go ahead first.
Okay, thank you. Thank you very much, Erik, for this nice talk. Since I'm not coming from condensed matter community, so I have a naive question about your experimental setup. Is it possible to apply an electric field, which is in addition to its, I mean, you said that your electric field is oscillating, okay? Then is it possible to apply an electric field which has some gradient in one direction of your sample?
That's a very interesting question. Yeah, so the oscillating electric field is, of course, the electric field of the photon. It is a very interesting question, and it's something that I've been thinking about. So basically what you're asking me is, can you apply a DC offset to this?
Yes.
Yes, I can. I've never done it, and I'm not sure if it actually gives a difference.
To my understanding, the first consequence of such setup could be some momentum dependence in your, at least, theoretical formulation. For example, this sigma could depend on some momentum.
Yeah, but I think
then,
I think the offset that you would give is very small compared to actual momenta in the of electrons. So let's say crystal momenta. Yeah, so you give some offsets, but that's some average, and that's going to be very small compared to crystal momenta. So I don't think that's a large effect.
Doesn't it depend on the ratio of omega over gamma in the Dorodum model? I mean, I agree that if this ratio is a small, yes, we fall into this Dorodum regime, and so maybe momentum cannot contribute significantly. But how about the omega over gamma being of order 1, for example?
Well, then you're doing exactly the experiment that I'm showing you.
Right? Oh, okay. So you mean?
So let me just give me 1 sec. Oh, sorry, this slide is showing the wrong thing. Yeah, sorry, it's hidden behind. So 1 over, gamma, the width of this blue function.
Yes.
That corresponds to the half width of the blue curve, or the maximum of the red curve. And so you can read it off here. The photon energy, or the frequency of with which I'm oscillating the electrons, is exactly equal here to the width of my Drude function. So omega to gamma over gamma is exactly 1 here.
Then don't you expect to see some diffusive effect in addition to this Drude, response?
No, I guess not, because momentum here is very small, right?
Yeah, right.
But
charging.
Sorry.
Go ahead, please.
No, momentum of a photon is 1/100th or 1,000th of the actual momentum of an electron in a lattice, right? I mean, the wavelength of the change of the electric field is here. It's 10 micrometers.
Right.
Whereas the unit cell, or the inverse width of your Brillouin zone, is a few angstroms. So that sets the difference in scales of the momenta of the photon as compared to momenta of the electrons, and so you're not transferring any momentum with your photon.
I see. Mm-hmm. Okay. Yeah. Thank you.
Any other questions? Well, maybe while people still think about it, maybe you could go to the last slide where you made a comment on the, and maybe I misheard you, but you mentioned in the last slide, in the summary slide, you showed that there is and maybe this is not connected, but the puzzle at low T and high B. And you mentioned that Hall response is measured in strong magnetic fields. And I think there was some statement that you made about a puzzle that is connected to that. So is this connected to the last line that you?
Yeah, so maybe going back to one of the
Yeah. Sorry, because I missed that.
something is happening in the Hall density. Now the Hall density is measured by forcing a current through this material while applying a magnetic field. So then you get a Lorentz force, and you measure the voltage that develops perpendicular to the direction in which you're applying the current. Yes. So you get a transversal voltage, and that transversal voltage you can translate into a Hall resistivity. And the Hall resistivity is proportional to 1 over the carrier density in a very naive, simple picture.
And just
Okay.
to connect this to, so this is the Hall resistivity or Hall conductivity, which also has an anomalous contribution. Is that right? Anomalous in the sense of Haldane, there's some anomalous velocities that I think in terms of, if you think about kinetic theory. Is that
Okay, so I don't think people even consider this. No.
Oh, okay. So then, sorry. Then I'm so. But what then is, how is eta H defined? Sorry. So it's
N. It's just carrier density. So the Hall in a very simple. If you just take a very naive model where you just take electrons in a magnetic field, just from the Lorentz force, you get that the Hall resistivity, which is defined as voltage over current that you apply, is equal to 1 over NE, where N is the density of electrons and E is their charge. So this is just very basic textbook stuff.
Okay.
And people apply this to the cuprates. But in order to measure this, you have to apply a magnetic field.
And the
magnetic
are 2 plus 1 dimensional layers, right? And layered and
yes,
so you
have layers.
Have an out of plane magnetic field that you apply.
Exactly. And the fields that are being applied are very large. So they are, it's up to 30 Tesla, which is a really large field. And so the question has been whether in these large fields, the cuprates can still be considered, the same as they are in zero field. There may actually be other effects that happen in high magnetic fields that, give some response which has nothing to do with the physics of electrons in zero field. That's possible. And so you see in high magnetic fields, you see that there is something happening in the carrier density. Well, assuming a very simple model, basically a simple metal. In zero fields, something is happening as well. That's what the photo emission experiment says. But this is a completely different measurement and has nothing to do with the carrier density. And then if we go to my optics data at the very end, here, for example, in optics, in zero fields, you measure the carrier density directly. It's the area under the optical conductivity. It's just the prefactor in the Drude response. Sorry, it's not on this slide, but anyway, that's the blue data points here. And you see that nothing happens as a function of doping. It's just a continuous trend, no matter how you analyze the data. And that's confirmed by at least one other group. So nothing really seems to happen. And so the idea is that either magnetic fields introduces something in addition that we don't understand, or the interpretation of the Hall voltage data is simply not so simple. And you may need to write it in a slightly different way, and maybe something else is changing. Maybe not the carrier density, but for example, the transversal scattering rate, which does not necessarily have to be the same as the longitudinal one. And so that's what my data, at least what I hope to have contributed, is to that discussion in particular.
Thank you. And based on the data that you have, and you probably have a good understanding if your material is in a regime where electron scattering or phonon scattering is preferred or dominant. So because I have in the back of my mind if a theory like hydrodynamics could be applicable, or if there is some other effective description that could be applicable.
Yeah, I've given that a lot of thought.
Or are the samples just too dirty? Because I know it's very difficult to get them into a regime.
Yeah, I think so. I mean, and then you run into other problems. I mean, there is definitely electron-phonon interaction, and the electron, sorry, that has the dynamic coupling strength essentially is very large in the, or at least is strongest. Let me put it like this: whether it's large or small is the wrong word. It's the largest in the low energy range. You know, it's definitely not on the scales where I'm probing it. I'm probing large volumes, macroscopic volumes. I don't think you can see hydrodynamic effects.
Mm-hmm.
It's simply not the case. And I think for, you know, if you just do back of the envelope estimates, you need to go to samples that are 10, 20, 30 nanometers in size. And maybe if you do transport experiments in such small samples, you could start seeing hydrodynamic effects.
Mm-hmm. But maybe some general lessons that we learned from hydrodynamics in strong magnetic fields, or more generally in anisotropic systems, could apply. Because I mean, in the end, all you would need is an effective field theory for charge conductivity, and those all played by the same rule. Call them hydrodynamic or whatever you want to call them. They are basically an expansion in terms of operators that obey the symmetries of your system. So like but what we learned from that is, I'm asking that because it sounds very much like what people have been studying in the strong magnetic fields effect on hydrodynamics, and so there's a lot of stuff that you can understand just purely by symmetries.
Yeah, it's a very interesting question. I don't know the answer at the moment. I'm actually, one of the things that I'm doing, I'm going to do in the coming year, I hope, is to extend these experiments to much higher temperatures. Because I think at higher temperatures, we may see other effects. So the work of Blaise Goutereau, for example, where they look at this pinned charge density wave response that comes out of hydrodynamics. That's something that you probably would see at higher temperatures, because there you kill the Drude response, and then you're left with just this response. So that's one of the things I'm working on at the moment. But I would have to repeat most of the experiments I've shown you today, so it's quite a bit of work.
That's great, thank you. Yeah, are there any more questions? If that is not the case for the official part, then let me stop the recording. After thanking Erik again, thank you so much for being with us. Thank you everyone for the questions.
It was a pleasure. Thanks for having me.